In the last video, I talked about a characterization of UFDs which said that if R is an integral domain in which factorization terminates, then it's a UFD if and only if every irreducible element is prime. Using that, we showed that PIDs are UFDs. And our next order of business in the study of UFDs is to show that ZX is a UFD. And I started the discussion at the end of the last video in which I said that the goal really is to consider QX. Q is the quotient field of Z. In QX, we know that UFD property holds because Q is a field, QX is a polynomial ring in one variable over Q, which is a PID, hence it's a UFD. So in particular in that ring, every irreducible element is prime. Every element in ZX can be thought of as an element of QX. So we are going to use that and somehow conclude that in ZX also every irreducible element is prime. And I ended the last video by the remark that this analysis and the proof that we are going to present today works exactly in the same way for any UFD R, not just Z. And at the end, when we conclude ZX is a UFD, that analysis also shows that Rx is a UFD as soon as R is a UFD. So let's begin today by considering the following definition. So our whole video today is about keeping track of what is integer polynomial, what is rational polynomial, whether something is true in ZX, is it true in QX, if something is in QX, is it true in ZX, and so on. So in order to clarify all these things, we are going to define the following. So a polynomial in ZX, so let's say polynomial fx. So I'm going to usually just denote polynomials by f instead of fx. Just in the beginning I will write this. A polynomial fx in ZX is called primitive. This is a very important word for us, primitive, if the following happens. If the degree is positive, that means we are excluding all constants. We are not going to call constants primitive. So it must be at least degree 1 polynomial, and so it has two properties. The first is that degree is positive. It has three properties really, we will show that. GCD, I will explain this, A1 AN is 1, this is the second condition, and AN is positive, this is the third condition. What are these AIs? These are just the coefficients of f. So I am going to write f as AN xn, AN minus 1 xn minus 1 plus A1x plus A0. So remember, AIs are all integers because I am taking an integer polynomial. So these are integers. I want three things for a primitive polynomial. N is positive, that means the degree is positive. The GCD of all the coefficients is 1 and the leading coefficient is positive. So what are the examples of this? For example, if you take 2x squared plus 3x plus 1, is it primitive or not? It is primitive because degree is 2 positive, the leading coefficient is 2 positive, GCD of the coefficients, which is 2, 3 and 1, is 1. Whereas if you take minus 2x squared plus 3x plus 1 is not primitive because it has two of the three properties but not the third. The leading coefficient is negative, so that violates this condition. So AN has to be positive. The GCD is 1, degree is positive, but the leading coefficient is negative, so this is not primitive. Similarly, we have 2x squared plus 4x plus 2. Here also it's not primitive because leading coefficient is positive, degree is positive, but the GCD of the coefficient is not 1 because GCD is 2 here. Similarly, 4 is not primitive, 1 is not primitive, 4 is not primitive for many reasons. Degree is not positive, GCD of the coefficients is not 1. Whereas 1, GCD of the coefficients is 1, but the degree is not positive. So just a primitive polynomial is nothing but a polynomial of positive degree with positive leading coefficient, and there is no common divisor for all the coefficients. Very simple, right? So that's what a primitive polynomial is. So and we make the following easy remark. So the remark is, if Fn is as f is as before, An xn, An minus 1, xn minus 1 plus a1x plus a0, and let's say n is positive, an is positive. So these are the two of the three conditions. The degree is positive, leading coefficient is positive. Now when is f primitive? We can characterize that by saying the following: f is primitive if and only if f is not divisible by any prime integer. Right? All we want is that, so because we are assuming degree is positive and that leading coefficient is positive, primitiveness is simply the remaining property, which is that the GCD of the leading coefficients is 1. That means no prime number divides all the coefficients, which is same say if it divides all the coefficients, that means it divides f. If a prime number divides f, it means it divides all the coefficients, because if f can be written as p times g, that means p divides each coefficient an. So p dividing f is equivalent to p dividing each coefficient. If that doesn't happen, so in other words we do not want this to happen, then it's primitive. This second condition can be further characterized. Recall that we have the natural, I'll write that here, recall the map phi p from zx to z mod pzx. Remember, there is a natural surjective homomorphism from z to z mod pz. In general, for any ring R and any ideal I, we have a natural surjective homomorphism from R to R mod I. So here we have zx to z to z mod pz first, then we just attach a variable. So zx to z mod pzx. Here what are we doing? We take a polynomial and we just view this mod p. Right? So for example, if p is 3 and the function sends, let's say, phi 3 of 3x squared plus 2x minus 7 or plus 7 goes to 3x squared plus 2x plus 7 bar, which is 3 is, so this is like 3 bar x squared plus 2 bar x plus 7 bar. So this is actually just 2 bar x plus 1 bar. This is just a digression, right? We are just going modulo p for each of the coefficients. So 3x squared plus 2x plus 7 under phi 3 maps to 2, the leading coefficient goes away because 3 is the leading coefficient, and what survives is 2 bar x plus 1 bar, because 7 is 1 in z mod 3z. So if f is not divisible by any prime integer p, that means phi p of f is not 0 for any prime integer p. Right? Because if every coefficient of f is divisible by p, which is same as saying f is divisible by p, then the image of f under fp will be 0, because we are going modulo p for each coefficient. If each coefficient is divisible by p, that means the polynomial itself becomes 0. That means if phi pf is 0. So if phi pf is not 0, that means at least one coefficient of f is not divisible by p. That means f itself is not divisible by p. So this is a convenient way of remembering how to check that f is primitive. And this leads to the most important lemma in this video and in this whole proof that Zx is a UFT is the following. It's called Gauss Lemma. It's very simple, but it is very important. I will also remind you that a primitive polynomial is by definition an integer polynomial. Remember, the definition of primitive is it's an integer polynomial with 3 additional conditions. So primitive polynomials are automatically integers. So the Gauss lemma says that let f and g be 2 polynomials in the integer polynomial ring. That means f and g are integer polynomials. If f comma g are both primitive, then the product fg is primitive. This is a very simple and easy to verify fact, but it has this name Gauss lemma because it is extremely useful. It is applied all the time. So it's not saying very surprising fact, right? If you have 2 polynomials which are both integer polynomials and which are both primitive, then their product is primitive. Okay, some conditions are trivial because if f and g have positive degree, fg has positive degree. If f and g have positive leading coefficient, their product also has positive leading coefficient. Okay, so the proof of Gauss lemma says that degree of fg is degree of f plus degree of g, right? Because if x squared is the leading term of f, x power 4 is the leading term of g, when you multiply them, x power 6 will be the leading term of fg. So the degree is 2 plus 4. And f and g are primitive, so that means degree of f is positive, degree of g is positive, so the sum is positive, degree of fg is positive. So what is the leading coefficient of fg? If you think about it, if you for example multiply 2x squared minus 3x plus 6 or plus 3 times 5x power 4, 5x power 6 minus 7x plus whatever, the leading coefficient is the coefficient of the largest degree term. Here it is 2, here it is 5. So if you multiply them, you get 10x power 8. And we are not interested in what happens next. So the leading coefficient of fg is the leading coefficient. So I am going to write this as LC of f times LC of g. LC stands for leading coefficient. LC of fg is LC of f times LC of g, because leading term of fg is just the leading term of f multiplied by leading term of g. So leading coefficient has this property. But we know that leading coefficient of f is positive, leading coefficient of g is positive, so leading coefficient of f is positive. So it only remains to show that the GCD of coefficients of fg is 1. Equivalently, that's the third condition, right, of primitive polynomials. But as we observed here, once the degree is positive and leading coefficient is positive, primitiveness is characterized by phi pf is non-zero for any integer p, prime integer p. So fg is primitive if and only if phi p of fg is not equal to 0 for all prime integers. If you notice, I am using the word prime integer because now that we have notion of prime elements in an arbitrary ring, I won't refer to primes in Z as prime integers. So we want to show phi p fg is non-zero, right? If that happens, p does not divide all the coefficients of fg. That means the GCD of all the coefficients of fg is 1. So we want this to be true for every prime integer p. But the important thing now is phi p is an homomorphism of rings. So phi p of fg is same as phi p of f times phi p of g. So we want this product to be non-zero. But if this product is non-zero, that means now we use the fact that z mod pzx is an integral domain. Right? Z mod pz is in fact a field, so it's an integral domain. When you attach a variable to an integral domain, it remains an integral domain. It's a simple fact, right? If you multiply two non-zero polynomials over an integral domain, the product is also non-zero. So in an integral domain, when is the product non-zero, that means phi pf is non-zero and phi pg is non-zero for all p. Remember that in an arbitrary ring, two non-zero elements can multiply to 0. So it's not equivalent to this statement. Product non-zero is not equivalent to individual facts not 0. But in an integral domain, product non-zero if and only if the individual terms are non-zero. But now, what is the meaning of phi p f not equal to 0 for all p? That means f is primitive and g is primitive. For phi p not 0 for all p, that means because g is positive degree polynomial with leading coefficient positive, g is primitive if and only if p p g is non-zero. But these are hypotheses, right? We are given that f and g are primitive. So this proves that product of primitive polynomials is primitive. This is a very important thing for us. So if you have two primitive polynomials, their product is also primitive. So let me now continue and prove the next important proposition. So the proposition says the following. So I will write this down and give some examples after this. So let f be a rational polynomial now. Okay, so fx is in qx, and suppose degree of f is positive. Then f can be written as uniquely as, this word uniquely is extremely important for us, can be written uniquely as a product f is equal to CF0, where C is actually a rational number and F0 is an integer polynomial, is primitive. Okay, so what we have is f can be written uniquely as a product of a rational number and a primitive polynomial. Further, C belongs to Z. The C is in general a rational number, but C belongs to Z if and only if fx itself belongs to Zx. Okay, C belongs to Z if and only if fx is in Zx. Remember, we started with a rational polynomial. The C that we get is an integer if and only if the rational polynomial is in fact an integer polynomial. So the definition is C, remember this is a unique factorization. So C is something uniquely attached to a rational polynomial. C is called the content of f. So this is called the content of f. So before I prove this, let me first give you an example. So let's take fx to be, I'm going to take this 1 by 12 x power 4 by time minus 1 by 6 x cubed plus 1 by 3 x squared minus 2x plus 1 by 2. Remember, this is a rational polynomial. It's not an integer polynomial. Coefficients are rational numbers and they are not integers. So how do you write f as c times a rational number times a primitive polynomial? It's very simple. So first we can actually clear the denominator. So we will consider 12f to be x power 4 minus 2x cubed plus 4x squared minus 24x plus 6, right? So clear denominator to get an integer polynomial. Now see if that integer polynomial is primitive or not. Is this primitive? It is, right? Because it's positive degree 4, leading coefficient is 1, which is positive, and the coefficients have GCD 1 because one of the coefficients is 1. So f is, this is our f0. So now f can be written as 1 by 12 times f0. So this is C. So the content of fx is 1 by 12. So in this example, content is 1 by 12. So exactly the same process we now perform. Okay, so there is nothing strange here. So remember, we have to do two things. Given any rational polynomial, we have to show that it can be written as a product of a rational number and a primitive polynomial, and we also have to show that it's unique. So let's prove proof of the proposition. So there are two parts. First we will do existence, which is the easy part. What is the existence of the factorization? So what do we do? First, clear denominators to write. So f is given to us. So again, keep in mind this example. So I have taken an example here. Clear denominator means multiply by the GCD of the LCM of all the denominators. So multiply by some d to get df is equal to f1 in zx. Right? That's what we have done here. Multiplied by 12 to get an integer polynomial. So here in general I might multiply by whatever d it is. So clear denominator. So df is equal to f1 in zx. Now factor out the GCD of the coefficients of f1. So f1 is an integer polynomial. You look at all the coefficients. In that example, the GCD happened to be 1 itself, so we don't need to factor. But maybe there is something else, some common factor. So we can write this as E times f0. GCD is equal to E, let's say, E times f0. So I have an integer polynomial, all the coefficients have GCD E, so I pull it out. Then it clearly follows that f0 is primitive. Right? Is that clear to you? Because f0 has the same degree as f1, which is positive. Right? The polynomial f is positive degree, we are assuming. So multiplying by integers does not change the degree of the polynomial. So degree of f1 is positive, degree of f0 is positive. Also the leading coefficient of f0 is positive because the leading coefficient of f1 is positive. We are going to assume that degree of f is positive, and when you f may have negative leading coefficient, but when you clear out the GCD always picks out the negative part, and f0 now has leading coefficient positive. So it has positive degree, positive leading coefficient. And because we have factored out the GCD, the remaining coefficients have no common factor. So we can show that f0 is primitive. So just to correct what I said a couple of minutes ago, I factor out the denominator, I clear the denominator in such a way that assume that LC of f1 is positive. So I can assume that LC of f1 is positive, because if f has negative leading coefficient, I can adjust that in D to make sure that leading coefficient of f1 is positive. Once the leading coefficient of f1 is positive, leading coefficient of f0 is positive. So f0 is primitive, right? Because we have factored out all the common factors and put it in E. So now we can write E as E by D times f0. So this is going to be C, which is the content, and this is the primitive, right? So we have written f as a rational number. Remember, C is defined to be E by D, and it is in Q. As this example shows, content is in general not an integer. It is an integer if and only if f is an integer polynomial. Here we have started with a non-integer polynomial, so the content is actually a non-integer. It's a rational number which is not an integer. So we have written this as some rational number times a primitive polynomial. So this is the existence. We have to now show uniqueness. Uniqueness is also easy. So let us take f is a rational polynomial, and suppose f can be written as C times f0 and at the same time as D times G0. And what is the property of C, D, f0, G0? C and D are in Q, they are rational numbers, and f0, G0 are primitive. Primitive by definition means integer polynomials. So we have two possible descriptions. We would like to show that they are exactly the same description. In other words, we want to show C is equal to D, f0 is equal to G0. So let's show that. What we now know is that by clearing denominators, we can assume C, D are in Z. So what I am really doing is, I am looking at this equation C f0 equal to D G0, and by multiplying by some common factor, common denominator, I can write this clear denominators. I am basically writing C prime f0 equals D prime f0. For example, if you have 1 by 12 f0 times 1 by 7 G0, what I am doing is just multiply by 84. So I get 7 f0 is equal to 12 G0, okay, as an example. So now I forget f really. I have an equation and multiply by some common denominator, and now C prime, D prime are in Z. So I can again rename them and call them C and D. So I will assume without loss of generality that C and D are in Z. So we have CF0, DG0, F0, G0 primitive. That means they are integer polynomials. C, D are integers. Originally they are rational numbers, but now I have cleared denominators to make them integers. Let's say coefficients of F0 are AI. Remember, F0 and G0 have the same degree because a constant times F0 is equal to a constant times G0. So they are the same degree. So the coefficients are an minus 1, a0. Similarly, coefficients of G0 are, let's say, bi. Because F0 is primitive, GCD of AI is 1. Similarly, G0 is primitive, implies GCD of BI is 1. Right? F0 is an primitive polynomial. In this example, x power 4 minus 2x cubed and so on is a primitive polynomial. So A4 is 3, A3 is 2, A2 is 4, A1 is minus 24, A0 is 6. The GCD of all these coefficients is 1. But what are the coefficients of CF0? This is just CAI, right? We are multiplying every coefficient by C. Multiplying F0 by C means every coefficient by C. So the coefficients of CF0 is CAI. What are the coefficients of CG0? D0 rather. DG0 is BI. DBI. Because BI are the coefficient of Z0. DG0 has coefficients DBI. Since, okay, so two things to say now. What is the GCD of CAI? GCD of AI is 1. So the GCD of CAI is C. GCD of DBI is D. So you have a bunch of integers who are coprime to each other. That means the GCD is 1. You multiply all of them by the same integer. The GCD becomes C. So GCD of 4, 7 and let's say 9 is 1, right? Because they have no common factors. But if you multiply all of them by 5, so you have 20, 35, 45. The GCD will become 5 because 5 certainly divides all of them. No other integer can divide them, no other prime. So it is GCD 5. So AIs have GCD 1, so CAIs have GCD C. Similarly, DBIs have GCD D. But we now use the important fact that CF0 is equal to DG0. That means the set CAI is equal to the set DBI. Right? CF0 is the same polynomial as DG0. That means the coefficient sets are same. CAI is equal to DBI. But once the coefficient sets are same, their GCDs are same. Okay, so except that there is some confusion about positive negative. So what we can say is that C is equal to plus minus D, because if the GCD is 2, minus 2 is also GCD. Any associate times GCD is also a GCD. GCD is just greatest common divisor. We are now trying to do this in general. In integers, typically convention is to show that, define that GCD is positive. But in general, for an arbitrary ring, UFD, GCD is just the largest common factor. So any such thing multiplied by an associate is also going to be a GCD. And remember the remark at the beginning of this video. I am trying to show that ZX is a UFD, but the same proof carries over for any UFD R and shows that Rx is a UFD. So I am only going to use that C is equal to plus minus ID. Once C is equal to plus minus ID, and we know that CF0 is equal to DG0, that means F0 is equal to plus minus G0. C and D are actually same plus minus of same number. So we can cancel C, and only issue would be that maybe F0 is minus G0 or F0 is actually equal to G0. But in fact now we know that, note that leading coefficient of F0 is positive, leading coefficient of G0 is positive. Why is that? That is because F0 and G0 are primitive polynomials. By definition, a primitive polynomial has leading coefficient positive. So leading coefficient of F0 is positive, leading coefficient of G0 is positive, that means F0 is equal to G0. They can't be negative of each other, right? Because if F0 is minus G0 and if F0 is leading coefficient positive, then leading coefficient of Z0 has to be negative. Because if 2x squared minus 7x plus 1 is F0 and G0 is minus F0, it will be minus 2x squared plus 7x minus 1. But then the leading coefficient is negative, which it cannot be. So F0 must be G0. Okay, so F0 is equal to G0. Once this happens, C equal to D also, because CF0 is equal to DG0. F0 and G0 are same, so C and D are same. So originally we said C and D are possibly negatives of each other, but that cannot happen. We have concluded that C equal to D. So this shows that the expression of any arbitrary rational polynomial into its content times a primitive polynomial is unique. Okay, so this is the proof of this proposition. So in this example that we did before we proving this proposition, this particular rational polynomial has content C 1 by 12 and F0 is the primitive polynomial. In other words, what we have now shown is that there is no other expression. Every time you write it as a content as a rational number times a primitive polynomial, that rational number has to be 1 by 12 and that primitive polynomial has to be this x power 4 minus 2x cubed and so on. So in general, every rational polynomial can be written as a product of its content, which is a rational number, and a primitive polynomial. Now that there is actually the proof is not quite complete, because the proof also says that C is in Z if and only if Fx is in Zx. This is now easy, right? Because we have written F as C times F0. So suppose F is in Zx. If F is in Zx, we know that F0 is also in Zx. That means, and F0 has no common factors. Coefficients of F0 have no common factors. So if C is not an integer, that means C has a denominator which is not 1. But that denominator cannot be cancelled by any of the factors of F0. So C must be Z in Z itself, because if C is not in Z, that violates the fact that F is in Zx. Similarly, if C is in Z, that is easy. If C is in Z, F0 is also in Zx, so F is in Zx. This now completes the proof. So if you take a rational polynomial, find its content. If that content happens to be integer, then the rational polynomial is actually an integer. Similarly, if you take an integer polynomial, write its content, then that content must be integer. So that's what we have shown. Okay, so let me stop the video here. In this video, we defined primitive polynomials and we proved a very important theorem called Gauss Lemma, which says that product of primitive polynomials is primitive. And then we have shown that every rational polynomial can be written as a rational number times a primitive polynomial, and that rational number is called the content. And final remark I will make in this video is that everything that we have done in this video carries over to any UFD, not just Z. You can replace Z by any UFD R, and all the definitions and theorems we gave today carry over to that. So in the next video, we will prove finally that Zx is a UFD, and more generally, if R is a UFD, Rx is a UFD. Thank you.